Imagine a scientific idea, I mean, a really big one, that once just glittered with incredible promise, you know, daring to think machines could think like us.
Yeah, really fundamental stuff.
Then picture that same idea just sort of fading away, hitting this wall of skepticism, maybe even outright dismissal by the scientific mainstream.
Yeah, pushed to the fringes.
But here's where our story takes this truly fascinating turn. It didn't just vanish. It staged this spectacular, world-reshaping comeback.
It really did.
That, today, is the amazing journey we're diving into. The return of the neuron to the absolute core of artificial intelligence.
It's a fantastic story. For decades, the whole concept of artificial neurons, which was, a foundational idea for AI way back, it became almost, well, the scientific pariah.
Like something you didn't talk about in serious circles.
Pretty much. By the early 2000s, the idea of general intelligence powered by these brain-inspired structures, it was often met with ridicule, honestly, in academic circles. It was considered very much a fringe theory. Yet right then, precisely during that time, this quiet but really profound revolution started brewing.
Okay.
And it was driven by this convergence, this perfect storm. An unprecedented surge in computational power, the emergence of vast new data sets, and critically, some truly clever, ingenious algorithmic breakthroughs.
Right, the secret sauce.
Exactly. And these allowed researchers like, the big names, Hinton, LeCun, Bengio, to start demonstrating capabilities that the old school, traditional rules-based AI, well, it just couldn't touch.
So our mission for you today is to give you a clear, hopefully compelling narrative of this pivotal shift. We'll walk you through its initial, almost giddy promise, right?
Yeah, the early excitement.
Then the painful periods, the so-called AI winters when, interest and funding just dried up.
A really tough time.
And then we'll shine a light on the key ingredients that fueled the neuron's resurgence. You'll uncover those aha moments, the specific innovations that took this discarded theory and made it the dominant paradigm.
Yeah, transformed it completely.
We want to give you a real shortcut to understanding why AI looks and feels the way it does today. We're going to trace how that increasing computational power, those massive data sets, and the crucial algorithmic refinements breathed new life into neural networks.
Taking them from skepticism back to excitement.
Exactly, and cementing the neuron's central role. Okay, let's begin this deep dive. All right, so our story kicks off way back at the absolute dawn of this idea, long before, modern digital computers were even a thing you saw everywhere.
We're talking the 1940s, 50s, a really different era.
A time of incredible theoretical leaps. And the initial spark, the very beginning, came in 1943 from two really visionary researchers, Warren McCulloch and Walter Pitts.
That's right, McCulloch and Pitts. They laid the theoretical groundwork, and what's fascinating is how they pulled together ideas from really different places.
Like what?
Well, first, the basic physiology of neurons in the brain, how brain cells seem to work. Second, a formal analysis of propositional logic, true-false statements. And third, Alan Turing's groundbreaking theory of computation.
Wow, okay, so brain science, logic, and the theory of computers all blended together.
Exactly. What's truly remarkable is how they synthesized these fields to conceptualize their artificial neurons.
So what was their model? What did it look like?
Well, what McCulloch and Pitts did was, honestly, revolutionary in its simplicity, but also its scope. Their model basically pictured each artificial neuron as a simple binary switch. It was either on or off.
Okay, simple enough.
But here's the crucial part. A neuron would only switch on if it received enough excitatory input from its neighbors, right? If it crossed a certain threshold.
Makes sense, like a tipping point.
Precisely. And this on-off state, they argued, was, and I quote, factually equivalent to a proposition which proposed its adequate stimulus.
Okay, unpack that a bit.
It basically means they directly link their artificial neurons, these simple on-off switches, to the true-false states of formal logic. This allowed logical operations like and or not to be mapped directly onto how the network behaved.
Ah, so you could build logic circuits out of these neuron-like things.
Yes. And even more profoundly, they mathematically demonstrated that networks of these simple units, if you connected them right, in layers, could compute any computable function.
Whoa.
Yeah, it's a direct echo of Turing's idea of a universal machine. This wasn't just, an interesting parallel. It established this fundamental theoretical link between brain-like structures and the very essence of computation. And this was long before we had the actual machines to build them.
That's incredible, just laying the pure theoretical foundation.
Absolutely.
And the innovation didn't stop there, right? With just the basic neuron model?
Not at all. Just a few years later, 1949, Donald Hebb comes along. And he introduces a concept that, I mean, it's echoed through decades of AI research. It's still foundational today.
Okay, what was that?
A simple yet really profoundly influential rule for modifying the connection strengths between these artificial neurons, what we now call Hebbian learning.
Hebbian learning. I've heard that phrase. Neurons that fire together, wire together.
That's the famous postulate, exactly.
Yeah.
It basically means if two neurons are active at the same time, the connection between them should get stronger.
So it's learning from association.
Precisely. This was a really early, really crucial attempt to give these networks the ability to learn directly from data, from experience, to adapt and form new connections based on patterns, rather than being explicitly programmed for every single scenario.
You really have to stop and think how audacious this all was back then. I mean, imagining computing machines that mimicked not just the brain's structure, but also its learning process.
And doing it long before digital computers were common. It's amazing.
This theoretical foundation was just absolutely critical, wasn't it? Setting the stage for everything that came after.
It absolutely laid the intellectual groundwork, no question. And from these theoretical beginnings, we pretty quickly moved into an era of, well, intense public excitement and real optimism.
This is the perceptron era.
Exactly, the perceptron era. In the 1950s and 60s, Frank Rosenblatt's perceptron, it just captured the public's imagination.
What was the idea behind the perceptron?
Rosenblatt designed it as a device that could make decisions by summing up evidence from, as he put it, many small experiments. There was this strong sense of, I don't know, romanticism around it.
Yeah.
Oh, yeah, a real buzz around these attractive and exciting new ideas that were swirling through cybernetics and these early pattern recognition machines. The scientific community, and honestly the broader public too, they were just captivated by the prospect of machines that could actually learn.
And crucially, these weren't just ideas on a blackboard, right? They actually built things.
They did. Researchers built actual analog hardware implementations. These early perceptrons, they used components like motor-driven variable resistors to adjust the connection weights, the adaptive parameters.
The little knobs turning automatically.
Sort of, yeah. And they used simple camera systems, often just arrays of photo sensors for the inputs.
Wow. And what could these early machines do?
Well, they were built to perform some pretty fascinating tasks for the time, like discriminating simple geometric shapes or recognizing handwritten characters.
So telling a square from a triangle, that kind of thing.
Exactly, that kind of thing.
Yeah.
And while they were obviously limited in scope compared to today, these tangible demonstrations of learning machines were incredibly captivating. They really hinted at this future where machines could perceive and understand the world.
But there's always a but in these stories, isn't there?
There usually is. With this initial wave of enthusiasm came the first really serious practical hurdle. One that would, frankly, plague AI for decades.
And that was?
What Richard Bellman, back in 1961, called the curse of dimensionality.
The curse of dimensionality sounds ominous.
It was, and still is, a major challenge. As researchers tried to move beyond these simple toy problems, squares and triangles, and increase the number of input variables, the dimensions of the data, traditional methods, just struggled profoundly. The amount of data you needed to make meaningful predictions started to grow exponentially with each new dimension you added.
So if you wanted to recognize more complex images with more pixels, you needed vastly more examples.
Vastly more. It meant that your data became incredibly sparse in these high-dimensional spaces. It was hard to find enough examples close together to learn meaningful patterns. This led to really poor representations of the underlying structure, making any attempt at general learning incredibly difficult, borderline impossible sometimes. It was a fundamental barrier to scaling these early neural networks.
Okay, so the complexity just exploded. And this leads us towards disappointment, right? Towards the first AI winter.
Exactly. Here's where the story takes a rather dramatic downturn. In 1969, two highly influential figures at MIT, Marvin Minsky and Seymour Papert, published their book, simply titled Perceptrons.
And this was the big critique.
Oh, it was a sharp, decisive critique. For many people, it just poured cold water on the whole burgeoning field of neural networks. Their argument was powerful. They said, look, while perceptrons do okay on these simple toy problems, there was, and I quote them again, no theory to explain what made the difference, particularly when they seemed to work well on small problems but broke down with larger problems of the same kind.
So they lacked a theory for why perceptrons failed to scale up.
Precisely. And they didn't just make vague claims. They offered specific, rigorous mathematical proofs of the perceptron's inherent shortcomings.
Like, what kind of limitations did they prove?
Well, the most famous example is probably showing that a single-layer perceptron, even one with a limited receptive field, was fundamentally unable to determine whether parts of a geometric figure were connected or not.
Connectedness. Like, is this one shape or two separate shapes?
Exactly. Which seems like a relatively simple concept for us humans, right? And it's a crucial primitive for any kind of general vision system. If your system can't even tell if something is connected, how can it understand complex scenes?
That does sound like a pretty fundamental flaw.
It was seen that way. Their work was viewed as the definitive statement, and the impact was, frankly, devastating for neural network research. It contributed significantly to a long period of deep skepticism. Funding dried up, research attention shifted elsewhere. This was the first real AI winter.
And the whole idea of brain-inspired AI got pushed aside.
Largely, yes. The very idea of machines having general intelligence through these kinds of architectures was often met with considerable ridicule. By the early 2000s, neural networks were widely considered a fringe theory, almost, laughed out of the room by many prominent computer scientists.
Wow, it's such a classic, almost heartbreaking story, isn't it? You have this early, fervent enthusiasm,
So much promise.
and it just hits this seemingly insurmountable wall of practical and theoretical limitations.
Exactly. And it's important to remember, it wasn't necessarily that the core idea of artificial neurons was wrong. It was more that the tools weren't ready.
Yeah.
The computational power just wasn't there. We didn't have the sheer volume of data needed. And critically, our collective understanding of how to train complex, multi-layered networks, well, it just wasn't sophisticated enough yet for the really hard real-world problems. The promise was grand, but the tools were insufficient.
Okay, so we've seen the initial burst of excitement, the groundbreaking theory, and then this really deep disappointment, the AI winter. Let's now turn our attention to how things started to change, to the quiet revolution that paved the way for the neuron's big comeback.
Right, because despite those AI winters, which really stretched through the 90s and into the early 2000s.
A time when, as you said, progress felt achingly slow and neural nets were mostly ignored.
Exactly. But something truly extraordinary began to brew, sort of beneath the surface. The concept of the neuron, this brain-inspired idea, was about to stage its triumphant return.
And it wasn't like one single magic bullet, right? You mentioned a convergence.
No, not at all. It wasn't one eureka moment. It was really the powerful convergence of three critical factors coming together at the right time.
Okay, so let's break those down. What was the first pillar of this revival?
The first pillar, and perhaps the most foundational in some ways, was just the sheer explosion in computational power.
Moore's law in action.
Moore's law, absolutely. The exponential growth in computing capabilities meant that the really complex, repetitive, computationally intensive calculations that neural networks demand, well, they just became increasingly feasible.
Because training these things takes a lot of number crunching.
A huge amount. We're talking about the ability to handle massive computational loads that were simply unthinkable before. Those early neural networks, they just couldn't scale effectively because the hardware wasn't there to support the millions or eventually billions of operations needed to train them on meaningful, large-scale problems.
So the raw processing power started to catch up with the ambition of the idea.
It really did. It shifted neural nets from being largely a theoretical curiosity back towards being a practical possibility.
But it wasn't just about individual chips getting faster, was it? There was something else happening with hardware.
You're absolutely right. Faster individual processors helped, but the real game changer was parallel processing. This became absolutely crucial, especially with the rise of something initially designed for a completely different purpose: graphics processing units, GPUs.
Right, the things that make video games look good. How do they help AI?
Well, it turned out that GPUs, originally designed for rendering complex graphics, were almost perfectly suited for the kind of math neural networks do.
How so?
Think about it. A neural network involves countless simple mathematical operations, mostly multiplications and additions happening simultaneously across many, many connections. GPUs, with their architecture of thousands of small, specialized cores working in parallel, could just blast through these operations far more efficiently than general-purpose CPUs, which typically have fewer, more powerful cores designed for sequential tasks.
So they could do many simple things at once, which is exactly what neural nets needed.
Exactly. And techniques like data parallelism became a cornerstone.
Yeah.
This is where you split your training data into chunks and process different chunks simultaneously across multiple GPUs.
Speeding things up significantly.
Massively. This allowed for much larger batch sizes during training, which often helped stabilize the learning process, and it dramatically sped up the entire training cycle, often by a factor roughly proportional to the number of GPUs you could throw at the problem.
And as these models got bigger and needed even more GPUs, getting the GPUs to talk to each other efficiently became important too, right?
Precisely. To truly scale these systems, especially for the enormous models we see today, you needed fast interconnects. Things like NVLink and InfiniBand played a vital role. They enable seamless high-speed communication between dozens, sometimes hundreds, of GPUs, whether they're in one machine or spread across a computing cluster.
Okay.
This hardware evolution allowed researchers to tackle models and datasets of a scale that would have been utterly impossible just a decade before.
It's hard to overstate that jump. For you, the listener, imagine trying to, I don't know, bake 1,000 complex cakes using just a tiny toy oven.
Right.
It would take forever if you could even do it.
Right.
Now, imagine suddenly having access to a giant industrial-grade multi-rack bakery oven. That's kind of the leap in capability AI researchers got with GPUs and parallel computing. It wasn't just faster, it enabled a fundamentally different scale of work.
That's a great analogy. It really changed the game.
Okay, so that's pillar one, exploding computational power, especially parallel processing with GPUs. What was the second pillar?
Pillar number 2, and I'd argue it's equally foundational, was the deluge of data, specifically labeled data.
The explosion of labeled data, why was this so critical?
It's difficult to overstate its importance. This explosion provided neural networks with an unprecedented scale of real-world problems to learn from. Think about datasets like ImageNet.
Right, the famous image dataset.
Exactly. ImageNet contained millions, eventually over 14 million images, meticulously hand-labeled by humans into thousands of categories, everything from specific breeds of dogs to types of vehicles.
And the labeled part is key here.
Absolutely crucial. This wasn't just any data, it was labeled data, which is the essential ingredient for supervised learning. That's the main paradigm, where a network learns by comparing its predictions to known correct answers, the labels.
So it needs examples with the answers attached.
It does. Before these large labeled datasets became available, researchers often had to painstakingly create their own small, custom datasets. This severely limited the complexity and generality of the problems networks could learn.
Right, you could only train it on what you had time to label yourself.
Exactly. The availability of these massive, diverse, human-annotated datasets allowed networks to learn much more robust features and patterns that actually generalize well to new, unseen data. They could move far beyond simple shapes or limited toy examples and start learning about the complexity of the real world.
And there's an economic aspect to this data too, isn't there? It's not just a technical resource.
Absolutely not. Today, we understand data is, well, often costly to acquire, right? Collecting it, cleaning it, labeling it takes significant effort and resources. But prediction machines, these AI models, cannot operate without it. It's the fuel.
The raw material.
It is. It's essential not only for creating and training the models initially, but also for operating them and continuously improving them over time. Think about a real-world example like the company Cardiogram. They wanted to predict strokes using heart rate data from wearables.
Okay.
To do that effectively, they needed heart rate data from thousands and thousands of users. And specifically, they needed examples of abnormal heart rhythms linked to conditions like atrial fibrillation, which increases stroke risk. That specific labeled data was critical for training their predictive models.
So the volume and the quality of the labeled data let the neural networks find subtle patterns.
Exactly. Patterns that had remained entirely hidden from previous, more rules-based AI approaches or simpler statistical methods. Without this massive influx of data, even the most powerful hardware and the most clever algorithms would just be sitting idle, inert.
That makes perfect sense. You can almost think of it like this. A human brain learns by experiencing millions, maybe billions of examples from the world's sights, sounds, language, interactions.
Right. Continuous input.
Early AI models, constrained by data scarcity, had maybe a handful of examples in comparison. They were starved for input. Then came the internet, digital cameras, social media, the whole digital explosion.
Yeah, generating data on an unprecedented scale.
And that provided the vast, rich, diverse sensory input that these artificial brains, these neural networks, desperately needed to finally start learning effectively and generalizing to the real world.
Couldn't have said it better myself.
Okay, so we have compute power and massive labeled data. What was the crucial third pillar?
The third pillar, without which the first two wouldn't have had nearly the same impact, was algorithmic refinements. in entirely new network architectures.
Ah, the clever
The
ideas.
clever ideas, exactly. This is where the brilliant minds came back into the picture, specifically tackling the fundamental limitations that people like Minsky and Papert had pointed out decades earlier. It wasn't just about making the old ideas run faster on new hardware with more data. It was about inventing fundamentally new, more sophisticated ways for these artificial neurons to connect, learn, and process information.
And these new methods were designed specifically to handle the scale of the new data and the available compute power.
Precisely. They were tailored for this new reality.
A key figure here, instrumental in this revival, was Geoffrey Hinton. His work in the early 2000s seems pivotal. Can you tell us more about his breakthroughs?
Hinton's contributions, often with his students and collaborators, were absolutely transformative. They essentially breathed new life back into the field, which became known as deep learning. His papers, like Trading Products of Experts by Minimizing Contrastive Divergence in 2002, and perhaps even more famously, A Fast Learning Algorithm for Deep Belief Nets in 2006, were really pivotal.
What was the core problem they solved?
One of the major challenges holding back neural networks was effectively training networks with many layers, what we call deep networks. The standard training algorithm, backpropagation, which adjusts weights based on errors, it just struggled with deep architectures.
Why was that?
It often got stuck in poor solutions, what we call local minima, or it suffered from the vanishing gradient problem, where the error signal becomes too weak to effectively update the weights in the earlier layers of the network.
So the learning signal fizzled out before it reached the bottom layers.
Exactly. Hinton and his colleagues developed clever pre-training techniques. For instance, using restricted Boltzmann machines, or RBMs, stacked together to form deep belief networks, or DBNs.
Okay, what did that achieve?
These techniques allowed individual layers of the network to be trained efficiently first, often in an unsupervised way, just learning patterns in the data without labels, before the entire network was fine-tuned using supervised learning with backpropagation.
Ah, so it gave the network a better starting point.
A much better starting point. This layer-by-layer pre-training initialized the network's weights into a much more sensible region of the parameter space. This allowed backpropagation to then work much more effectively, enabling the network to learn the complex hierarchical features needed for difficult tasks. These papers really marked a profound turning point. They showed how to overcome the key challenges of training deep, multi-layered neural networks and made them genuinely effective.
So it wasn't just about adjusting based on errors, but finding a smarter way to begin the whole learning process for these deeper, more complex architectures.
That's a great way to put it. And alongside Hinton, another pioneer, Jan LeCun, had also been working on foundational improvements for years. For example, he'd been refining methods like backpropagation learning with second-order methods, way back in 1989.
Second-order methods. What's the difference from standard backpropagation?
Okay, so standard backpropagation uses the first derivative of the error function, the gradient, basically the slope, to figure out how to adjust the weights. Second-order methods go a step further and incorporate information about the curvature of the error landscape mathematically, the Hessian matrix.
So not just which way is downhill, but how steep the curve is.
Exactly. This allows the optimization algorithm to take potentially more efficient, sometimes larger steps towards the minimum error. It can help speed up convergence and often find better solutions, especially on the complex, bumpy, non-convex error surfaces you get with deep networks.
So these were fundamental improvements in the optimization process itself, how the networks actually learn.
Yes. These foundational improvements in how networks learn from their errors, how they adjust their internal weights to get better predictions, became even more critical as networks started getting significantly larger and deeper thanks to the compute and data. They provided the mathematical backbone for efficient and stable learning in these much more complex structures.
So it sounds like the algorithms were iterating smarter, not just faster, navigating this complex landscape of possible solutions more effectively.
Precisely.
And all this led to a new generation of network architectures, moving decisively beyond the simple perceptrons that Minsky and Papert had critiqued.
Absolutely. Instead of those simple single-layer perceptrons, the focus shifted dramatically towards architectures with multiple layers, like multi-layer perceptrons, MLPs, and also things like radial basis function networks. The key innovation was the inclusion of hidden layers between the input and output layers.
What did these hidden layers allow?
They allowed the networks to learn and represent incredibly complex nonlinear relationships in the data. They do this by essentially combining or superimposing the outputs of these hidden functions or hidden neurons which themselves adapt to the data during training.
So they could model much more intricate patterns than a single layer could.
Far more intricate. The breakthrough was that these multi-layer architectures could learn these complex, nonlinear mappings between multi-dimensional input spaces and output spaces, something single-layer perceptrons provably couldn't do for many important problems, like the connectedness example.
And crucially, did this help with the cursive dimensionality problem?
It did, significantly. While the models became much more complex internally, the number of parameters, the weights that need to be learned in these newer architectures, often grew only linearly or perhaps quadratically with the dimensionality of the input data.
Okay, linear or quadratic growth, not exponential.
Exactly. Which was a vast improvement over the exponential growth of parameters or data requirements that had plagued many earlier approaches and contributed to the curse. It was an ingenious way to manage the complexity, allowing the models to scale to higher dimensions without exploding, effectively sidestepping one of the biggest limitations that Minsky and Papert had so eloquently pointed out decades before.
Okay, so the stage was meticulously set. We had the three pillars: immense computational power from GPUs, vast labeled data sets like ImageNet, and these clever new algorithms and deep architectures from researchers like Hinton and LeCun. The Neuron was ready for its comeback tour.
Ready to reclaim its central role, absolutely. And this led to truly groundbreaking results that just profoundly reshaped the entire landscape of AI.
One of the most visible, most talked about moments has to be 2012, the ImageNet moment. This seems like a genuine revolution in image recognition driven by convolutional neural networks, or CNNs. Tell us about that.
The ImageNet moment in 2012 was, without exaggeration, a watershed event for AI. Alex Krzyzewski, working with Ilya Sutskever and Jeffrey Hinton at the University of Toronto, used a deep convolutional neural network, which they called AlexNet, to compete in the ImageNet large-scale visual recognition challenge.
And they didn't just do well, they blew the competition away, right?
They absolutely did. The result was groundbreaking. Previous methods, which mostly relied on painstakingly handcrafted visual features, were achieving error rates around 25–26% on this tough benchmark. AlexNet slashed that error rate down to just over 15%.
Wow, a 10% absolute drop. That's huge in a competition like that.
It was a stunning improvement, a qualitative leap, not just an incremental gain. It shocked the computer vision community. Remember, ImageNet was this massive benchmark data set designed to be really challenging. AlexNet's success powerfully demonstrated that these deep CNNs could automatically learn highly effective discriminative features directly from the raw pixel data, without needing humans to pre-specify what features to look for.
So it learned how to see, in a sense, rather than being told what details mattered.
That's a great way to put it. And the impact, as you hinted, was immediate and profound. CNNs rapidly became the new gold standard
For all sorts of image tasks.
for a whole wide array of image-related tasks. Sophisticated object recognition, definitely, but also object detection, drawing boxes around objects, image segmentation, labeling every pixel, image captioning, medical image analysis, you name it. If it involved images, CNNs became the go-to approach almost overnight.
And this success also fueled a trend towards making these networks even bigger, right? The deeper is better idea.
It did. The success of AlexNet, which had 8 layers, quickly sparked this idea. If deep works, maybe deeper works even better. Researchers started building much deeper architectures. Networks like VGGNet pushed it to 16, 19 layers. Then came ResNets, or residual networks.
That's right. Those got incredibly deep.
Astonishingly deep. ResNets with 50, 101, even 152 layers became not just feasible to train, but consistently outperformed shallower networks. They could learn richer, more hierarchical representations of visual information, from simple edges and textures in early layers to complex object parts and entire objects in later layers.
But training in networks that deep, hundreds of layers, surely that brought back the vanishing gradient problem with a vengeance. How did they make that work?
That's an excellent question, and it required another key innovation: skip connections, which were central to ResNets.
Skip connections, what do they do?
Imagine the normal flow of information going layer by layer, undergoing transformations at each step. A skip connection creates a shortcut. It takes the input from an earlier layer and adds it directly to the output of a later layer, effectively letting the signal skip over several layers in between.
Okay, like an express lane for the information.
Sort of, but more critically, it's an express lane for the gradient during training. When backpropagation calculates the error signal to update the weights, these skip connections provide a direct path for the gradient to flow back to earlier layers without diminishing as much through repeated transformations.
Ah, So it helps the learning signal reach those crucial early layers in very deep networks.
Precisely. It effectively mitigates the vanishing gradient problem, ensuring that even the earliest layers receive a strong learning signal and can be trained effectively. These skip connections, or very similar ideas, proved so useful they also appeared in other successful deep architectures, like dense nets, and significantly later in transformers as well. They are fundamental to making extremely deep learning possible.
It's incredible. For you, the listener, just picture this. Suddenly, machines could see and categorize objects and photos with accuracy that wasn't just matching humans, but often exceeding human performance on specific tasks. This ImageNet moment, powered by deep CNNs and innovations like skip connections, was where a lot of the lingering skepticism around neural networks just seemed to evaporate, almost overnight for many people. It truly put the neuron back in the spotlight for visual understanding.
Absolutely, a pivotal moment.
Now, beyond static images, AI also needed to grapple with sequences, things that unfold over time, like language, speech, music, or even financial data. This led to another really crucial family of neural networks, recurrent neural networks, or RNNs, and a specialized variant called long short-term memory, LSTMs.
Oh.
How did RNNs try to handle this temporal context?
RNNs became really popular for sequential data precisely because their architecture was designed to handle time. Unlike standard feed-forward networks where information just flows straight through from input to output,
Right, no loops.
RNNs have internal loops. These loops allow them to pass information from one step in the sequence to the next. Essentially, the output of the network at time step 2 depends not only on the input at time step 2, but also on the network's internal state, or memory, from time step 2-1.
So they have a way to remember what came before.
Exactly. They maintain a form of memory, allowing them to consider previous inputs when processing the current one. This ability to carry information forward through a sequence was a major advance for tasks where context that unfolds over time is critical, like predicting the next word in a sentence based on the preceding words, or understanding a spoken command where the meaning depends on the whole phrase. They were explicitly designed to model these temporal dependencies.
Okay, that sounds like the right tool for the job. But I seem to recall RNNs had their own big challenge, especially when dealing with long sequences. You mentioned vanishing gradients earlier. Did that pop up again here? It's something called exploding gradients.
You recall correctly. The very nature of recurrence, while powerful for capturing short-term dependencies, actually made the vanishing and exploding gradient problems even worse when dealing with longer sequences.
Why was that?
It comes down to how RNNs are trained, typically using an algorithm called backpropagation through time, or BPTT. To calculate the updates, the error signal needs to be propagated backwards through potentially many time steps, essentially unrolling the loop.
Right.
Now, if the weights in the recurrent connections are small, less than 1, multiplying that small weight by itself repeatedly as you go back through time causes the gradient signal to shrink exponentially. It vanishes.
So the error signal from the end of a long sentence barely influences the weights responsible for processing the beginning of the sentence.
Exactly. The network fails to learn long-term dependencies. Conversely, if the recurrent weights are large, greater than 1, the gradient gets multiplied by large numbers repeatedly and can grow exponentially. It explodes, leading to massive weight updates and unstable training. The whole learning process can just break down.
So simple RNNs struggled to connect events that were far apart in a sequence.
They really did. This limitation was a major hurdle, and that's precisely where techniques like long short-term memory, LSTM networks, introduced back in 1997 by Sepp Huckreiter and Jürgen Schmidhuber, and later simplified versions like gated recurrent units, GRUs, became absolutely game-changing.
LSTMs and GRUs. How do they manage to overcome these gradient problems where simple RNNs failed? You mentioned gating mechanisms.
Yes, gating mechanisms are the key innovation. LSTMs and GRUs introduce these sophisticated internal controls. Think of them like tiny learnable switches or valves that regulate the flow of information within the network's memory cell over time.
Okay, so they control what gets remembered and what gets forgotten.
Precisely. An LSTM cell, for instance, typically has 3 main gates: an input gate, a forget gate, and an output gate. The forget gate decides what information from the previous time step's memory state is no longer relevant and should be discarded. The input gate decides what new information from the current input should be added to the memory state. And the output gate controls what part of the current memory state should be passed on as the hidden state for the next time step and used for prediction.
Wow, so these gates are like little managers inside the neuron carefully controlling the memory.
That's a good way to think about it. And crucially, these gates are themselves controlled by small neural networks whose weights are learned during training. This allows the LSTM to learn, from the data, how to selectively retain important information over very long periods and forget irrelevant information, all without the gradients vanishing or exploding nearly as easily as in simple RNNs.
That sounds incredibly powerful, a robust long-term memory for sequences.
It was. These mechanisms effectively mitigated the gradient issues that plague simple RNNs, propelling LSTMs and GRUs to huge success in critical sequential tasks. Machine translation, speech recognition, sentiment analysis, handwriting recognition, you name it. They opened up entirely new applications for neural networks and understanding sequential data.
So for the listener, think again about understanding a long, complex sentence, or maybe following the plot of a movie, or even listening to a piece of music. You need to remember what happened earlier to make sense of what's happening now. LSTMs gave AI a much more powerful and stable way to handle that kind of long-range temporal context and dependency.
A truly significant step forward.
Okay, this is where things get, I think, even more interesting and lead directly to the AI systems making headlines today. The next massive algorithmic leap, especially for language, the transformer architecture. This emerged around 2017 and feels like the culmination of the neuron's return in many ways.
Absolutely. The transformer architecture, introduced in that seminal 2017 paper, Attention is All You Need, by Vaswani, and a team of researchers, mostly at Google Brain and Google Research.
Yeah.
It really changed everything, especially for natural language processing, NLP.
Attention is all you need. Quite a statement. What was the core idea behind attention?
Well, the concept of attention mechanisms had been brewing in the field for a couple of years before that, particularly in machine translation. The basic intuition is that when you're processing a sequence, say, translating a sentence, not all parts of the input sequence are equally important for predicting the next part of the output sequence.
Right, some words are more relevant than others at different points.
Exactly. Attention mechanisms provide a way for the model to learn to pay attention to the most relevant parts of the input sequence when generating each part of the output sequence. It calculates a set of attention weights, essentially saying how much focus to put on each input element. The researchers behind the transformer explored using this attention concept not just between input and output, but within the input sequence itself, self-attention, and within the output sequence. They experimented with using this to translate words more quickly and accurately.
But what was really radical, what seemed crazy to many researchers at the time, was that the transformer famously got rid of the recurrence, the loops, that were the defining feature of RNNs and LSTMs. How could it process sequences without recurrence?
It was indeed a radical departure, and yes, many were skeptical initially. Instead of processing sequences step by step, passing information along like RNNs, the transformer relies heavily on self-attention mechanisms.
Self-attention. How does that work?
In self-attention, for each element, say each word or token, in the input sequence, the model calculates attention scores with every other element in that same sequence. It essentially asks, how relevant is every other word in this sentence to understanding this specific word? These scores are then used to create a weighted sum of the representations of all words, producing a new representation for the target word that is context-aware, informed by its relationship to all other words in the sequence.
So every word can directly look at every other word simultaneously, regardless of distance.
Exactly, in a single parallel computation. This global perspective, often enhanced by using multi-head attention, where the model computes attention in parallel subspaces looking for different kinds of relationships, allowed the transformer to capture long-range dependencies much more effectively and efficiently than RNNs, which struggled to pass information accurately over very long distances due to the sequential processing and potential gradient issues.
And presumably doing this in parallel was much faster on GPUs than the step-by-step processing of RNNs.
Much faster during training, as the computations for all positions could be done simultaneously. There was still a need to ensure causality during generation. You can't look at future words when predicting the next word, and they handled this cleverly with a look-ahead mask. But it fundamentally broke the sequential bottleneck of RNNs, enabling training on much larger data sets and building much larger models.
And this radical architecture, this reliance on attention instead of recurrence, combined with truly massive data sets scraped from the internet and unprecedented computational scale, this led directly to the large language models, the LLMs, that are everywhere now, right? Models like GPT-2, GPT-3, GPT-4, BERT, etc.
Precisely. The transformer architecture's scalability, its efficiency in parallel processing, and its power in capturing complex dependencies in language data were the crucial enabling factors for these incredibly powerful LLMs. These models are, as the sources say, far more complex large language models based on training a neural net in very specialized ways.
And it's interesting you mentioned their underlying ideas trace back to Claude Shannon in the 1940s.
Yeah, it's a fascinating link. Shannon, the father of information theory, explored probabilistic methods for approximating language back then, basically, predicting the next letter or word based on the preceding ones. Today, LLMs are, in a highly sophisticated sense, descendants of that idea, using massive neural networks trained on vast amounts of text to learn the statistical patterns of language and predict subsequent tokens incredibly well.
And the capabilities that emerged were just stunning to many people.
They really were. The ability of these models to generate remarkably coherent, contextually relevant, often convincing text to write emails, summarize articles, answer complex questions, hold conversations, even write code was seen by many as somehow more impressive, perhaps more fundamentally intelligent seeming than previous AI achievements like image recognition or game playing, because it touched the core of human communication and knowledge representation.
This really felt like the moment AI learned to talk in a way that seemed natural, flexible, and surprisingly knowledgeable, moving far beyond the brittle, rule-based chatbots of the past.
It did. And it was this radical design choice ditching recurrence for attention that unlocked these incredible new capabilities, fundamentally changing how AI processes and generates human language, and giving rise to the powerful conversational agents and generative tools we interact with daily.
So the Neuron, via the transformer, had well and truly returned, demonstrating these unprecedented capabilities. And this led to a massive shift in public and scientific perception about what AI could actually do.
Absolutely. The abstract theoretical promise was finally translating into concrete, often astonishing results. Yeah. A prime example that really captured the world's attention even before the LLM explosion, DeepMind's AlphaGo.
Right, beating the world champion at Go in 2016, that felt huge.
It was a landmark moment for AI. Go is an ancient game, known for its incredible complexity and strategic depth, far exceeding chess. Many experts thought it would take decades more for AI to conquer Go, as it seemed to require intuition and creativity beyond mere calculation.
And AlphaGo didn't just win. It sometimes made moves that seemed alien, creative, yet ultimately brilliant, right?
Exactly. It demonstrated a level of strategic understanding and planning, learned through a combination of deep neural networks and reinforcement learning, playing millions of games against itself, that genuinely stunned the human Go world. This event garnered immense media attention. There was even that great Netflix documentary about it. It powerfully showcased the ability of deep learning to tackle problems requiring abstract reasoning and long-term strategic foresight, capabilities that traditional symbolic AI had always struggled with.
It really solidified the idea that these learning-based systems could achieve things previously thought to require human-like intuition.
It did. And then more recently, we've seen the LLMs like GPT-4 demonstrating astonishingly general capabilities across a huge range of domains.
You mentioned the standardized test results earlier. Can you recap some of those? They sound almost unbelievable.
They are quite remarkable. OpenAI reported testing GPT-4 on a diverse battery of standardized tests, from AP exams to graduate school entrance exams and even professional certifications. And it outperformed its predecessor, GPT 3.5, by a significant margin.
Like the bar exam.
Yeah, GPT-4 apparently scored in the 90th percentile on the uniform bar exam, whereas GPT 3.5 was way down in the 10th percentile. That's a massive lead.
And things like AP exams?
It reportedly achieved a top score of 5 in AP Calculus BC, both Physics 2 exams, U.S. History, Biology, and Chemistry. And perhaps most surprisingly, it apparently even passed the Certified Sommelier examination, at least the theory part, which is known for being incredibly difficult and requiring deep knowledge of wine regions, grapes, vintages, food pairings.
Okay, that's impressive and slightly terrifying. Now, the caveat is always there, how much of the test material might have been in its training data.
That's a fair and important caveat. The issue of potential cheating or contamination if answer keys or very similar questions were part of the massive web scrape it learned from. OpenAI acknowledged this challenge. However, the sources also emphasize that there's much more evidence of the capabilities of GPT-4 beyond test scores, its ability to reason, synthesize information, write different kinds of creative text, translate languages, write working code.
Right, the emergent abilities that go beyond simple recall.
Exactly. These systems, which were once dismissed as mere toys, unable to handle real complexity, had suddenly become very powerful very quickly. They were demonstrating a breadth and depth of understanding and capability that few people would have imagined possible just 2 decades earlier, when neural nets were largely dismissed. From being labeled snake oil to mastering Go and acing professional exams, the neuron had undeniably returned, planting itself firmly at the center stage of AI and fundamentally reshaping our technological landscape.
So we followed this incredible roller coaster journey, the initial promise, the long winter of skepticism, and then this stunning resurgence fueled by compute, data, and algorithms.
Yeah.
But let's step back now. What does this return of the neuron fundamentally mean? What's the bigger picture here for AI and for us?
I think it represents nothing less than a fundamental paradigm shift in how we approach building intelligent systems. We've moved decisively away from AI based primarily on pre-programmed explicit rules, the symbolic AI approach that dominated for decades.
Where humans had to figure out and code all the logic.
Exactly. We've moved towards systems that learn complex patterns and behaviors directly from vast amounts of data.
And you mentioned earlier that neural networks largely self-organize during training. That feels like a key difference from traditional programming. Can you elaborate on that?
Yeah, that's a crucial distinction. In traditional software engineering, a human programmer explicitly designs the algorithms, the data structures, the control flow.
Yeah.
Every function, every rule is deliberately coded with a specific purpose in mind.
Right. You know what each part is supposed to do.
With neural networks, especially deep ones, it's quite different. While we design the overall architecture, the types of layers, how they connect, the specific function of individual neurons or groups of neurons, and the intricate patterns of weights that emerge, those are largely determined by the learning process itself, by backpropagation, adjusting millions or billions of parameters to minimize prediction errors on the training data. There isn't a predetermined plan specifying which parts of it are supposed to perform the different functions.
So the intelligence is emergent, discovered by the network interacting with data, rather than explicitly encoded by a human.
Precisely. It resembles a process of self-organization and emergent intelligence, driven by the data and the learning algorithm, much more than traditional top-down explicit design. And this allows for a level of flexibility and adaptability, especially in messy, high-dimensional, ambiguous domains like vision or natural language, that rules-based systems simply struggle to achieve.
And this fundamental shift, this embrace of learning and emergence, is what has enabled AI to finally tackle problems that seemed completely intractable before. Problems characterized by complexity, nuance, maybe just the sheer difficulty of writing down all the rules for something like human-like intelligence.
Absolutely. Think back to that curse of dimensionality that plagued early perceptrons and other methods. This new paradigm, powered by deep learning, has found effective ways to handle it.
How so? How do deep networks manage the scaling problem?
The ability of deep neural networks to learn nonlinear mappings between multidimensional spaces by adapting those hidden functions in their layers is key. Instead of needing an exponentially growing number of examples or rules for every possible combination inputs, deep networks learn hierarchical representations.
Hierarchical, meaning?
They learn simple features in early layers, like edges or textures in an image, and then combine those features in subsequent layers to represent more complex concepts, like object parts, than whole objects. This hierarchical feature learning allows them to discover and exploit the underlying structure in high-dimensional data, discerning subtle patterns and correlations that will completely overwhelm a human trying to write explicit rules. They learn compact, effective representations of the data itself, which then makes the final classification or prediction task much easier, effectively taming or at least significantly mitigating that curse of dimensionality.
Okay, so they learn to represent the world more efficiently. And this leads to the idea that a lot of what modern AI excels at is basically prediction.
Yes, that's a really powerful framing, popularized by economists like Ajay Agrawal, Joshua Gans, and Avi Goldfarb in their book Prediction Machines. They argue that much of what modern AI, especially deep learning, does can be understood as prediction in a very broad sense.
Not just forecasting the future, but...
Right, not just forecasting, but using existing information you have to fill in, missing information you don't have. It could be predicting the category of an image, predicting the next word in a sentence, predicting the probability of loan default, predicting which ad a user will click on, or even predicting what move to make in a game.
And their point is that AI has made this prediction capability incredibly cheap and abundant.
Exactly. This cheapening of prediction is having profound economic and societal consequences. It's obviously making traditional prediction tasks like inventory management, demand forecasting, weather prediction, medical diagnosis much more accurate and efficient.
But it's also changing how we approach other problems.
Yes, it's enabling us to reframe entirely new problems as prediction challenges. Think about autonomous driving again. Instead of trying to program explicit rules for every conceivable traffic situation, which is probably impossible.
Yeah, good luck with that.
A common approach now is to train the system to predict human judgment. Essentially, what would a skilled, safe human driver do in this exact situation, based on learning from millions of miles of driving data? This prediction-based approach fundamentally alters how we conceive of and solve complex decision-making problems, making AI applicable in domains where rule-based systems were just too brittle or incomplete.
That's a really insightful way to look at it, prediction as the core capability.
It provides a very useful lens.
And even with this incredible comeback story, with the neuron firmly established at the center of AI thanks to these breakthroughs, the field isn't standing still, is it? It feels like it's evolving faster than ever.
Absolutely not static. It's in a state of continuous, incredibly rapid evolution. We're seeing ongoing algorithmic refinements building directly on these foundational neural network breakthroughs all the time.
Can you give an example or two?
Sure. For instance, we're seeing techniques like LoRa, which stands for low-rank adaptation. This is a clever method for parameter-efficient fine-tuning. Instead of retraining an entire massive LLM, which costs a fortune and requires huge amounts of memory, LoRa allows you to adapt the model to new tasks or datasets by injecting just a few small, trainable matrices into specific layers.
So you only update a tiny fraction of the parameters.
Exactly. It achieves comparable performance to full fine-tuning, but with huge savings in memory and computation, making it much easier to customize these giant models for specific applications or even run multiple specialized versions simultaneously. That's a very practical refinement.
Okay, that makes sense. Any others?
Well, in reinforcement learning, especially for aligning LLMs with human preferences, techniques like PPO, proximal policy optimization, have become really important. PPO helps stabilize the training process, preventing the AI's policy, its strategy for acting, from changing too drastically between updates, which can cause performance to collapse. It makes reinforcement learning from human feedback, which is crucial for making LLMs helpful and harmless, much more reliable and practical to implement.
So the innovation continues at a rapid pace, refining these core neural ideas.
Constantly. This is not a field resting on its laurels. It's incredibly dynamic, always building upon and refining these neural foundations, pushing the boundaries of what's possible almost weekly, it feels like sometimes.
So tying this all together for you, our listener, what does this whole journey, this return of the neuron, mean for you? Well, it means that the AI you interact with every single day, whether it's doing an image search on Google, talking to Siri or Alexa, using translation tools, seeing content recommendations, or maybe even chatting with an advanced LLM like ChatGPT or Claude, all of that is fundamentally shaped by this deep, complex, sometimes quite dramatic history we've explored today.
That's right. Understanding this story, the early dreams, the winters of doubt, the crucial convergence of compute, data, and algorithms, and the key breakthroughs like CNNs, LSTMs, and transformers helps you grasp why AI seems to be advancing so rapidly right now. And it gives you a much better sense of what these systems truly excel at, and perhaps also where their limitations might still lie. It's the backstory to our current moment. #TagOutro.
We have covered a lot of ground today. We journeyed from those earliest sparks of artificial neurons lit by McCulloch and Pitts way back in the 1940s, and the elegant theoretical brilliance of Hebbian learning.
The very first attempts to model learning.
Then through the long, skeptical shadows of the AI winters, where the whole idea faced doubt, even ridicule.
A period where progress seemed stalled.
But then we witnessed that powerful, almost perfect storm. The convergence of immense computational muscle thanks to GPUs, the absolute deluge of vast datasets fueled by the digital world, and those ingenious algorithmic breakthroughs driven by pioneers like Hinton, LeCun, Bengio, and the architects of the transformer.
A confluence that changed everything.
And that convergence brought the neuron roaring back from the scientific wilderness right into the mainstream, onto our phones, into our homes, and at the heart of the tech industry.
From the revolutionary CNNs that finally allowed machines to see and understand images with unprecedented accuracy,
to the sequence understanding power of RNNs, and especially LSTMs that let AI process language in time.
and finally, to that game-changing transformer architecture, using attention to power the large language models that are reshaping how we interact with information and technology today.
This deep dive, I hope, has shown how this once discarded, almost fringe idea became the absolute bedrock of modern artificial intelligence.
It really is a remarkable testament to scientific persistence, the sheer power of technological convergence when the timing is right, and maybe most importantly, the willingness of brilliant minds to revisit questions that others thought were long settled, to look again at ideas that had fallen out of favor.
Which brings us to our final thought for you today. So, if the neuron, this brain-inspired concept, made such a powerful and frankly unexpected comeback, enabling machines to learn, to recognize patterns, to generate text and images in ways that seemed like science fiction just a generation ago, it really raises an important question, doesn't it?
Hmm.
What other discarded or perhaps fringe ideas currently exist out there in science or technology? Ideas that might be facing skepticism, maybe even dismissal today, but are just waiting.
Waiting for their moment.
Exactly. Waiting for that right combination of enabling technology, maybe new data, or just fresh insight. Waiting for their own perfect storm to stage their own triumphant return and fundamentally reshape our world in ways we can't yet imagine.
It's a fascinating thought. What might be lurking on the fringes now, ready for a comeback?
What might you rethink as ripe for a comeback? Something to ponder.